So now we're going to calculate the standard deviation. We're going to do this using the tabular method. It's called the tabular method. And then I'm going to show you how to do it on your calculator in stat mode. Okay? So we're going to do this by example. Below is pocket money spent by a student for lunch or snacks over the past week. So you can interpret this as $2 was spent on Monday, $8 on Tuesday, $10 on Wednesday, $16 on Thursday, and $5 on Friday. Now, it's only 5 observations. Our sample size is 5. But from the observations, we need to make a decision. If I was to depict them graphically, there's not enough really to see anything. But what do I see? I see that if I put these in order, let's say I was to rank these numbers, I've got 2, and then 5, and then 8, and 10, and 16. Alright, so what you have is a middle value of 8, so some sort of center at 8, and then on either side of 8 there's a smaller value, and then there's a larger value, and they're both, 5 is 3 values from 8, 10 is 2 values from 8, so they're about the same distance. Further away we have 2 and 16. So 2 is 6 values away from 8, and 16 is 8 values away from 8. So they're about the same distance as well. So what I'm going to say is, I'm going to take a long shot and say I think that the pocket money spent is symmetrically distributed in general, and even though we just have a sample here, it reflects the general pattern. So because it is symmetric, I can be comfortable in calculating the sample mean x bar as a measure of center, and I can also calculate the spread measure as the standard deviation S. And here they are. We know this one. We've already discussed the sample mean. And what do we have here? Okay, so we're going to break down this formula so you never forget it. This is my goal. What is the standard deviation? The standard deviation is the square root of this thing. Inside here, this is called the variance. So let me write that down. This is equal to the square root of the variance. What is the variance? So the standard deviation is the square root of the variance. The variance is the average squared deviation from the mean. All right, what does that mean? We will know that by the end of this video, okay? Let's start making calculations deep inside. So we're going to begin here. We first need a mean. So let's get a sample mean. Let's make a calculation of a sample mean. We can do that with our calculator if we want, or simply sum without stat mode, adding these values together and dividing by 5. Okay? Or you can use stat mode. Remember how you do that, using the sigma key. So what do you get? In stat mode, I would punch 2, summation button, 8, summation button, 10, summation button, 16, summation button, and 5, summation button, and ask second function for the sample mean, and I get this is $8.20. So that is the sample mean. we have our center measure as the mean, the sample mean. What we're interested for measuring the spread is an idea of how spread out the values are. Okay, so we see, in fact, $8 we said was about center, and look at that, the sample mean is $8.20. Okay, so now we want a measure of how spread out the other values are. So what we got to do is calculate something called deviation from the mean. Okay, so how far is 10 from 8? That's 2. How far is 5 from 8? Well, that's -3. Okay, so how did I figure that out? I'm going to take each value and subtract off the mean to do that. Okay, in this case I was using the actual values, but let's use the sample mean instead. It's a better measure of center, more accurate. Alright, so let's make these calculations. 2 minus $8.20. We're going to take 8 minus $8.20. 10 minus $8.20. 16 minus $8.20. Oops. And 5 minus $8.20. And I'm going to put the values here, okay? So here are my computations of the deviation from the mean. That's what this column represents, deviation from the mean, the sample mean. The calculations could have been done the other way around, but as long as they're consistent, it doesn't really matter to make my point. All right, what's my point? Well, looking at the deviations from the mean, what's a good measure of spread for this data? Well, a good measure of spread for this data over here might be just taking the average of the deviations from the mean. What happens if you calculate the average, the sample mean of the deviations from the mean? In other words, add these all together and divide by 5. What do you get? Take a moment and do it. So what did you see? You should be adding these together and getting 0. So if you were to add them together and get 0, then dividing them by 5, you're still going to have 0. So what does that mean? Why is that happening? Well, remember our definition of the sample mean. The sample mean was the center of gravity. So the center of gravity is 8.2. 8.2 is in a position such that that distribution is balanced. Remember, I can balance the shape on a finger. So that means that there's equally as many observations in magnitude or density on the right side of the distribution as there is on the left. So in other words, the distribution is equally spread out around the standard, around the mean. It's equally spread out around the mean. So being equally spread out, if I just take the deviations from the mean on both sides, these will always sum to 0. So they cancel each other out. What's causing them to cancel is this sign. So what I really want to have is a measure of deviation, but I don't really care which direction it goes in. I'm interested in deviation from the mean, so I can actually drop the sign and average those values, but that's not the convention used in statistics. The convention used in statistics is to remove the sign by actually squaring the values. Okay, what will that do? Well, a negative 6.2 times negative 6.2 is a positive number. Okay, so a negative times a negative becomes a positive, and a positive times a positive becomes a positive. So you'll have eliminated all the negative signs, so there will not be any canceling. let's make the calculations in this column that are the deviations from the mean squared. Okay, that's all this is, the deviation from the mean. So the squared deviations from the mean. So here are the squared deviations from the mean. I just took each of the values over here and squared them to get these values, okay? Alright, so now what? I should just take the average of these values, right? Almost, but not exactly that. Let's look now at the formula for S, the standard deviation, the sample standard deviation. So here are the deviations squared, okay? And here is the sum of the deviations squared. Now remember what I told you about means. Means are identified by this symbol where we sum a bunch of values and then divide by how many there are. That's kind of what we have here. We're summing a bunch of values. Yeah, it's the deviation squared, but that's not the main thing. It's that we're summing a bunch of values and we're dividing by how many there are less 1. Okay? So if we wanted average square deviations from the mean, we should be dividing by n. What's happening is we're making an adjustment. Okay, we're making an adjustment because we have to consider the fact that when we divide it by n in calculating the average, we're dividing by how many values of randomness there are in computing the sample mean. Okay, there were n values of randomness, so we divide by n to give a representation of the average. Well, here in the standard deviation, there are n values of randomness, but because this value is an estimate in our calculation, we lose what's called a degree of freedom. So we go from n values of randomness, or n degrees of freedom, to n minus 1 degrees of freedom. Okay, so that's why we're dividing by n minus 1. What is happening? Well, we're dividing by a smaller number, right, because n minus 1 is smaller. When we divide by a smaller number than we would have if we divided by n, the overall number is a little bigger. What does this do? This ensures that our sample standard deviation covers the values and is a good representation of the spread of the values in the distribution. Okay, so let's see how that turns out in our interpretation of our result at the end. So what we have to do is we need to sum these values first and then divide by 1 less than n. Let's do that calculation. What we're going to do is calculate, I call it the average in quotations, because it's not exactly the average that we're used to dividing by n, but it's an average, right? Adjusting for degrees of freedom, changing to, being changed to 1 less than n. Okay, so let's get the average quotations of the squared deviations from the mean. So here we have our formula expressed as the variance, right? Because we said that average squared deviations from the mean is called the variance. So let's get the variance first. The sum of the squared deviations from the mean is 112.8. So we're going to take 112.8 and divide by 1 less than the sample size, so that's divided by 4. When you divide 112.8 by 4, you get 28.2. Are we finished? Well, we should be able to answer the question in the same units that the question was posed. What were the units of the original problem? Well, these were dollars, right? Dollar spending. So X is in dollars. The deviations from the mean, X minus X bar, is also going to be in dollars because we're taking X dollars minus the sample mean in dollars, so that gives you dollars back. But what happens here? We've squared dollars, so this whole column is made up of units of dollars squared. What does that mean? It really doesn't mean anything, so that's why I'm not going to put it here, and I'm not going to put it on the variance term. What I need to do is get back to the dollars. How can I get back to dollars? Well, since the units here are dollars squared, I need to take the square root. Hence, you understand why we take the square root of the variance. Finish this off then. S is equal to the square root of the variance 28.2, which is equal to $5.31. How do we conclude? We conclude with a statement that uses both the sample mean and the sample standard deviation. She spends about $8.20 on average a day, give or take $5.31. That's how we use the standard deviation. Because the distribution we're assuming is symmetric, we can make a statement like this and talk about how spread out the values are. Does that cover all of the values? Well, let's see. If we go between $8.20 back $5, what's 8 minus 5? It's about 3. Okay. And also, if we take $8.20 and we add $5, we go as far as 13. So we're covering most of the values in the range, but not all of them. Okay, so within one standard deviation, adding and subtracting one standard deviation, we get most of the values covered. And that's why an expression like $8.20, give or take 531, tells you about most of the data. The way I write this is 8.2 plus or minus $5.31. So I minus 531 from 8.2, and then I add it, and I get a range of values that I can write down as $2.89, comma, $13.51. And these are the values within one standard deviation. And they cover, like we said, most of the values. Okay, so that's a good description of center and spread of a symmetric distribution. I'd like to make two additional points. First about the degrees of freedom concept. I've written a couple of pages to explain and reason with you about the degrees of freedom being n minus 1. I won't test you on that, so you don't have to know that verbatim. I just want you to I want you to remember we divide by n minus 1, and I want you to remember the degrees of freedom are n minus 1, okay? That's all I really want you to remember. The rationale, it's up to you if you want to understand that, but I do provide you the information on it. One point, and I've said most of the things I've written in the subsequent notes, I just want to add, if we have a large sample size, dividing by, like, let's say 10,000, if you were to divide by 10,000 or 9,999, it wouldn't greatly affect this value anyway, so it's really a moot point. It's not really of a difference whether you divide by n or n minus 1 or large samples. The second point is, how do you do this in stat mode? Okay, well, essentially exactly the same way you calculate the sample mean, entering each value and then the sigma plus key, and then each value one at a time and the sigma plus key. And when you're finished, rather than asking for x bar, you're going to ask for the symbol sigma x n minus 1. That will give you s. Alright? There is another symbol on your calculator, but that would give you the calculation of this with divided by little n, not divided by n less 1. Alright? So really it's giving you the square root of the variance as though this was not a sample mean. Okay, and that's that. So you should verify that you can also get $5.31 in stat mode on your calculator.